Hello. In today's video, we'll be going over vectors, what they are, and how they apply to statics concepts. To begin, let's look at really what a vector is. So if we look at this basis system that I drew here, we notice if we let O be the origin, that we have this vector R pointing from O to some point that I'll call right here, point P. This is what we call a position vector. Vectors are a quantity that have both magnitude and direction. They are different from scalars, which simply just have a scalar value, no direction to them at all. So if we look at this vector in particular, its magnitude is essentially going to be the length, L, from point O to point P, and its direction is going to be defined by an angle from this axis right here, which I have called the I hat direction. Normally this will just be xy, like normal, but I'll call that theta. We can express vectors in terms of their magnitude and direction like this. I can rewrite this as r times r hat. R represents the magnitude of the vector, so in this case, r would be equal to L. And then r hat represents what is called a unit vector. A unit vector essentially has a magnitude of 1, but just tells you the direction that the vector is pointing in. It's equivalent to say that the unit vector is equal to the vector divided by its own magnitude, right? Because this corresponds to a unit of 1, a magnitude of 1. This vector right here is a unit vector, solely telling you the direction that it's pointing in. So I'll call this r hat. And if we were to just scale this roughly, we'll say that this length, the whole thing is 2, so that means this right here, roughly halfway, would be our r hat. So that's the basis of vectors, specifically position vectors. So let's look at an example problem and see how we would calculate these vectors and apply them to statics. So we have this system right here. We have a block and a roller attached to it. And at point A, we have two forces, F1 and F2, being applied as shown. We have our coordinate axes shown with X pointing to the right and Y pointing up like normal. And we know the angles relative to the X-axis for both F1 and F2. We want to find the resultant force at A from these forces. So the first thing we want to do is essentially write out an equation, a vector equation. We want to find the resultant force. We know that the resultant force is just going to be the sum of the two forces acting on point A, F1 plus F2. Now, since we're working in 2D, one vector equation is going to correspond to two scalar equations. What that means is essentially we can write this vector equation in terms of both of these directions for what we're given. Hopefully this will make sense in a second, but that's essentially saying we can write some of the forces in the x direction and some of the forces in the y, where these components, the component of F1 in the x and the y, are scalar values. So if we start with F1, we know that the x component, if I draw right here, is just going to be F1 times cosine theta 1. And then we can do the same thing here, plus F2 cosine theta 2. And this is going to be our resultant force in the x direction. Now if I do the same thing for the y, it's going to be F1, but now the y component is going to be the sine of theta, right? Based on this geometry, F1 times sine theta 1, and same thing for this, plus F2 times sine theta 2, and this is going to give you the resultant force in the y direction. And our resultant vector is essentially going to be this new vector of these scalar components, frx in the I hat direction, plus fry in the j hat. All right, so now I'm going to calculate these using my calculator and come back to you with the answers. Okay, so calculating the values, you get that frx is equal to 28.3 newtons and fry is equal to 51.0 newtons. Now, it's important to notice for this example that based on our coordinate system, F2 is actually, the x component is pointing in the negative x direction. So in this equation right here, it really just, and technically speaking, should be a negative sign. Make sure you catch your basis and what direction your forces point relative to that basis when you're computing vector equations like this. So the resultant force then is just going to be these scalars in a vector form. So it's going to be 28.3 in the I hat direction plus 51.0 in the j-hat direction. So this is our final answer for the resultant force in vector notation. Thank you for watching. I hope this video was helpful.